Okay, well, let's continue. So I will now give you a presentation about 45 minutes, an hour, on what patient-level prediction actually is. I'll be talking about, well, what it is and what it isn't, but also understand the whole modeling process. So how do we actually need to build these models? And then I'll show you some insights on a proof of concept study that we did a couple of years ago by now on patients with depression. So the whole story starts with patients having questions to their GPs, right? So it could be a patient that has atrial fibrillation and has seen in some papers that you could have a high chance of a stroke. And this specific patient may have that question, what is my chance of getting that stroke? And for the clinician, it's very hard to answer that question. So what often happens is that the clinician says, well, I don't have enough information, I cannot give you that exact prediction for your, based on your history. And that can often be a very good decision to say that, of course. However, what he could also do is quote an overall average for all patients, right? So we know that on average, patients with atrial fibrillation will get a stroke, let's say 10% of the patients. But that's, of course, for the average patient. It's not for that specific patient that he has in front of him. What he could also do is utilize knowledge and personal experience from other patients that he had in the same practice that looked like that patient and try to extrapolate that knowledge to the patient in front of him. It's a very difficult task because how can you, as a human, compare all the different covariates and all the different variables and elements in the electronic health record in a good way? It's very difficult. What you really need to have is a model, a personalized prediction model that we train on data that can support the clinician. And that's what we're looking into here. So it's about this problem that you talked about earlier. And it's important. It's at a moment in time using information in the history to say something about the future. In this case, that would be patients that got a atrial fibrillation diagnosis and then in predicting, for example, in the next year, the chance of having a stroke. Means we have to define these things, and during the day you will see how we're actually going to do this in the patient-level prediction package that we developed, how we define cohorts with Atlas, but also how we then run those studies using all the nice tools that we've been building in the last years. I want to start with explaining the difference between explanatory models and predictive models. And we're talking here about prediction. So it's not right to make causal claims based on the variables that end up in the models. And I think it's a very important insight that you need. Many people ask us, can you show me the variables in the model? And they make causal assumptions on those variables and think that if they would change that specific variable in the model, that they can change the chance of the probability of getting the outcome, which is not correct. And I'll talk a little bit about that. It all starts with different disciplines having a different understanding of the word model. So people coming from statistics think about the word model as describing a population. It's a distribution on the data. That's the first thing they think about when we talk about a model. Epidemiologists are thinking in causal inference, hypothesis testing. So defining a model automatically means looking at causality. While in data scientists and the machine learning world that we are active in, model is referring to a prediction model, predicting something in the future. And it's important that even if you come from these two different domains, that there is really a difference in how we use these models. And we already sent this to you in the homework, and I'm not sure anybody really looked into that, but I can really recommend these two publications. They talk about this in a lot of depth, and there's also a very nice video of Professor Smueli talking about this difference between to explain or to predict. And you really have to look into that. It's important information. I will talk a little bit about what she's saying in the next few slides, but there's a lot more to say about that, but we cannot go into it in this hour. So explanatory models are theory-based statistical models for testing causal hypotheses. So the strength, the power of the explanatory power of these models refers to the strength of the relationships in the model. In predictive modeling, we do empirical models for predicting new observations. So the power is how accurate are we to predict those new patients in the future? That's what we want to test. It's therefore important to realize that you can empirically evaluate the predictive power of such an explanatory model. You can apply it on data and see how well it performs. But the other way doesn't work. So you cannot empirically evaluate the explanatory power, so the causal effects in the model. To do that, if you really want to see the causal effect of a drug on the outcome, you again have to be in the other room and do causal inference and the population level effect estimation to compare two groups and correct for all the other bias and all the other confounders to be sure that the effect is related to that specific variable. It does mean that the best explanatory model that only contains causal effects that you have estimated and with using the other approach is necessarily the best predictive model. Because you can use more data, you can use all kinds of variables in your model and get a better performance, which may not contain all those causal factors that you know from literature. It's therefore also not always needed to understand all the causal effects to predict well. Right? So if you use a data-driven approach where you put in all the variables that you have and you have a very good prediction, you would like to use that model even though you don't necessarily need to understand all the individual variables. It may be good to take that model if a explanatory model would have like half the performance or a lot less performance. So it's also interesting, the table that is in that paper, where the steps that you take when building these models, so the analysis goal, the variables of interest, how you build a model, how you evaluate the model is different for these approaches. What we do is we use the data that's in our database. It's the data that we have at our hand. The variables that we put in the model are not driven by any journals or papers that discuss causal effects, but it's just the data that we have at hand and we learn from that data using a data-driven approach. The goal is to minimize the bias and the variance of the model, and we want to make sure that we don't overfit on our data. So that we build a model that works perfectly on our data, but if I give the model to somebody else and they run it on their data, the model is way worse. We want to find a way to learn from our data so we can export that data or transport the data to other data sources and get a good performance as well. So we measure the performance of our predictive models by looking at out-of-sample accuracy or area under the receiver operator curve. I'll get to that. But you use data that you have not used for training to evaluate your model. That's very important, to avoid that overfitting. And Jenna will come back later in the day also with some examples of what would happen if you would overfit on your data. This actually led to us thinking as a group on the term risk factor. So many publications talk about these are the risk factors in the model. And we have a bit of a problem with using the word risk factor because it automatically has some kind of causal thinking behind it, right? As if you can change the risk by changing that factor, which is actually not the case. Because what the models that we are training on our data, the variables that we select are based on their associative value. So how well are these variables associated with the outcome? That's not the same as causal, right? If our goal is to search for causal factors, we do the other course. If our goal is to search for association of individual variables, so just you want to know if that individual variable is an association with the outcome, you could actually do clinical characterization because you will just count in those patients with and without the outcome how often something occurs. It's just a descriptive study. What we want to do is build a model that contains multiple variables that are all related and try to find the best combination of all those different features to say something about the future. So what we, throughout the day, will do is we'll try to avoid the term risk factor and talk about predictors to make it very clear that the variables that are put in the model and that we use throughout the day is about a prediction, and it's not about association, so not risk factors. Another important insight is that and this is, I think, the only formula that I have on my slides. Maybe you have another formula, but we don't have many formulas. This is just a simple regression equation where you have a beta 0 and then you have weights for the individual variables that end up in the model. What's very important to realize is that each of these beta coefficients represent the additional effect of adding that variable to the model, keeping all the other variables constant. And why am I saying that? So that weight doesn't necessarily mean that if it's 2, that it's twice as important as one that's 1. It's in relationship to all the other variables that are inside the model. If you replace one variable, so let's say this is height that ended up in the model. If we now remove height, another variable may pop up and all the betas may change. Because it's under the assumption that the others are stable. And you need to think little bit about that. So if we find a model, it's not necessary that this is the only combination of variables that will end up in such a performance. There can be other variables we can replace variables in the model with other variables and get the same performance. So you need to be careful when you look at these models and saying that these are all the variables and that will explain why we get this outcome. No. It can be that some of these variables are highly correlated with other variables that may be the actual causal effect that we have not observed. So if you look at the beta values, if a beta is 0, meaning that that variable doesn't end up in the model, we actually don't know anything about that variable. We don't know if there's an association, because it may well be that there's another variable that's highly correlated with that one that did end up in the model. We definitely know nothing about causation, and that's actually true for all the beta values. If it's not 0, we at least know that there is an additive effect of that variable on the probability of the outcome. So there is a association there. Then the direction of these betas, if it's positive, it means it's only positive under the assumption of all the other variables in the model and all their beta values. So it can well be, and I've seen examples where the beta changes direction, so it goes from positive to negative when we change variables in the model, right? And it will take a little bit of time for you to think that through, but I hope you'll remember at the end of the lecture, when you look at these models, to keep that in mind. You should not make all kinds of assumptions when looking at these models without really understanding how the model has been trained on the data and how we generate these models. So you may wonder, why is prediction still valuable if we don't look at causal effects? Well, in general, I think it's a very critical question for a patient. What's going to happen to me with all my data? And you've seen that in these questions, and actually the questions that you all came up with are examples why prediction is valuable. Any questions on that before we move forward? Yeah, go ahead. Yeah.
I might be mistaken, but I thought the betas in the logistic regression, if you exponentiate them, aren't those not the relative risk of?
Yes.
Okay.
Yes, but they're under the assumption of all the other variables in the model, yeah. And that's the exactly. Exactly, yeah. But that's a very critical thing. So it's not that you can say that's a relative risk for that specific univariate variable. It's in a multivariable model. Yeah, correct. Okay, I'd like to move on. And as all of you know, and that's why there's also so much interest in our tutorials in the last couple of years, is that there are so many publications out there that do prediction modeling in different clinical domains. And what you see here is a Wordle where we did a query on PubMed, searching for all publications that say something about prediction, machine learning, that type of terms. And then we parsed, using some natural language processing tools, the diseases in those titles of those papers. And what you see here is the size of the word tells you something about the frequency of that specific clinical term being studied in these prediction papers. First of all, you see there are many different types of outcomes or clinical outcomes, but heart failure, cancer, lung cancer, stroke, diabetes, these are all domains that's a lot of publications. And you can see that this is an older review, but you can still see that there are 800 models that try to predict cardiovascular disease. There's also models for predicting stroke, 83 models in different publications for predicting stroke. Now, what's important to realize is that the problem that I showed you in the beginning was a patient with atrial fibrillation predicting stroke. We actually don't know, not from this slide, which of these models are in patients with atrial fibrillation predicting stroke. So there are a couple of them, I know that. Now, what's the problem with this is that there are so many models, but not many of these are actually used in clinical practice. And we'll talk a little bit about that, why we think that that's the case, and how we can improve that by building a framework to follow all the best practices in building these prediction models. An example is this one here, the CHATS-2 score. That is just a simple count of a couple of variables, and then you get a sum. And if the sum is above a certain number, you have a high chance of getting a stroke. This model has been used widely currently so by many, many clinicians, and there are different versions of it. There is a CHATS-2 vascular score, and there have been some updates. There have been some external validations as well being done by some groups. But it's one that's really used in clinical practice on a daily basis by thousands of clinicians. So what did they do here? If we look at our framework, they said patients newly diagnosed with atrial fibrillation who will get a stroke. It was in 1,000 days, and they used a logistic regression and using 5 pre-selected variables. So these variables in that model were selected based on consensus between a group of experts, and then they put these in the model and they estimated the beta values on the data that they had. Now, there are all kinds of questions from my side as a data scientist when I look at this. For example, why only these 5? What would happen if we would do a data-driven approach? Just use all the data that we have. How much better can we actually get to predict stroke? And so their approach was a kind of explanatory type of model. They put in variables that they thought that would be causal, and they tried to build a model using those variables. But what happens, what if that we have a model that could perform much better? Why are we not using this for our patients that could have impact? So these are things that we are looking into to make it possible to run these models, but also to externally validate them on many other data sets across the world. And if you look at this paper, and I think we put this also in the homework, or at least we gave you the link, this is a nice overview that looked at all kind of different prediction models and assessed what the current state of the field based on those papers. What you see overall is that many of these publications do not validate their model even on their own data. They just use all the data, they generate a model, they give performance measures, and that's it. They don't do a test-train split, so it's highly overfitted on their data, which is a bad thing. They often use small sets of features. Now that could be a problem. It could be that we can do better. We don't know, but it's definitely something we have to look into for all these models that are currently in clinical practice. Now we are in the more big data time. We have more data. We should try to see how much we can improve by using all the data and the computer power that we currently have. A third point, very important. It's very incomplete how people disseminate their models. So you have papers. People say we did a nice study, we run a logistic regression model or a lasso model, and it performs very well. Thank you. Nice. But I cannot find the model, I cannot download the model anywhere, I cannot run it on my own data, so I cannot validate the model at all. And I think that we should improve here a lot in the field. Everything should be available. If you publish a paper, the model itself should be somewhere on a website. I should be able to download it, run it on my own data, and return the results of on my data to that repository. So the papers become dynamic. We really think, and OHDSI throughout all our work packages, that we should think about kind of dynamic publications that don't stop at the date of publication, but continue by allowing the community to add more and more knowledge about that specific topic for the rest of the world. So we also will show you during the day how we tackle this problem. Transportability assessment is how well does my model perform on other data. It's always been very hard to do, so there are not so many papers out there that have evaluated that specific prediction model on tens or 20s of different data sources across the world. It's often 1, 2, maybe. And the reason for that is that the data isn't standardized. We have interoperability problem, that it's not easy to send somebody a model and ask them to apply it on their data, because we have to specify, we have to explain them how to define the cohorts, etc., etc. And with the Common Data model, we have the opportunity to improve a lot there, because we have that standard structure, we have the vocabularies, and we can send a package to them, run it on their data, and get the results back, all in a standardized framework. Impact on clinical decision-making. This is a very interesting area that much more research should be done in, actually, to really understand what happens to the patients if we put that model into clinical practice. What's the impact of that, of the use of that tool? So in OHDSI, we have been working hard the last years on building a framework for evidence generation, evidence evaluation, and evidence dissemination. So that the R package that we're going to talk about will have solutions for all these 3 different elements of predictive modeling. So how do we now build these models? It's the second part of my presentation. There are different steps in the pipeline. So it starts with problem specification. So we should have a study protocol that clearly specifies what's the question, and it starts with this description that we have here. Everybody should be able to get access to that protocol. And ideally, we want to have all analysis code that we run from the beginning of this pipeline till the end in open source, available on a website. We need to do data extraction. So we need to extract those 2 cohorts that we now selected on our common data model. And we can do that. We can do that with Atlas, and we'll show you later how to define these cohorts very easily. And then we can share the definitions of those cohorts with other data partners and generate these cohorts on their own data, using exactly the same definitions that we used in our original study. And of course, we need to extract data. So for the target cohort, we need to extract for all the patients in the target cohort all their variables, and then learn from all those variables in the data-driven way. So there's a nice package created by Martijn Schumi for feature extraction. So that you can run that, you can specify, this is my cohort in my CDM, in your cohort table. Give me for all those patients all these variables, so all observations, all drug use, everything. And it's a very flexible package, so you can select actually which elements or which domains you want to include in your study. And it will generate a kind of table like this with, at the end, also which of the patients got the stroke, so which patient got the outcome. And we use that type of table to train our models on. Now, training can be done currently in the package in 2 different ways. So you can do a person split, so you randomly assign patients to the train or the test set. Or you can do a time split, where you say everybody before this moment in time is in the training set, and everybody that's after that moment in time is in the test set. So this is I think it's a kind of better way of testing, because you literally don't use any information before, and you also assess. You assess actually what the effect is of time in your prediction problem, because the healthcare system may also change, and you may be able to assess that a little bit better when you use the time split. Now, then we have to make some decisions. which models are we going to train, and how are we going to evaluate these models. Now, models, algorithms is how I like to call them. So an algorithm will generate a model. We have different types of algorithms implemented in the package, and that is currently growing. But for example, it contains the regularized logistic regression, so that's just a regression, but it has an extra complexity term in the regression formula that tries to shrink all those beta values to 0, so it's doing automatically feature extraction on your data using a hyperparameter, and Jenna will get back to that. So this is a regression model. There are also tree models like random forest, which tries to build individual models, or multiple models, I should say. And each of these trees are built on a random selection of patients, so rows in the table, but also a random selection of the features, so the columns in the table. And the idea is that by combining like a lot of these small trees, you get a better performance because these individual trees can focus on specific type of patients. And the ensemble, or the combination of all the individual trees, could perform better. And there are some nice results on that, actually. The random forest it can be very powerful. The other one is gradient boosting, also a decision tree type model. It has multiple trees, but then you reweight all those elements that go wrong in that specific tree, give them a higher weight, and try to build a model that works better on that specific set of patients. Both have as core a simple decision tree structure. Now, there are many other models out there, K-nearest neighbors, native Bayes, and all kind of ADA boost, kind of boosting algorithms, and of course neural networks and deep learning. Everybody heard about that. We also implemented deep learning into our package. But the question now is, which of these models are we now going to pick for this specific question? Now, there is actually not an answer to that question. That's my answer. And the reason is that it highly depends on the data at hand, which of the models works better. And that's what we call the no free lunch theorem. So there is not one model or one algorithm that we can use for all our prediction problems and assure that this will work best. It's something that we have to assess on our data. And therefore, it's common practice that we try multiple models in our training phase and then decide on the model that we want. It can also be driven, of course, by considerations of complexity, or that you want to have smaller models, that kind of consideration. You may drive some of the decision choices, but in principle, the best is just to do the whole battery, see what works best, and then use that specific one. So that means that the strategy that we currently take is that we have a list of algorithms that we want to try, and we often start with lasso logistic regression because we empirically actually showed that for most problems, lasso is performing pretty well. There may be situations where the others improve or are a little bit better, but it's never, we have never seen until now situations where lasso is way worse than all the others, like 20% difference in AUC, for example. That we did not see that. So we always start with lasso just to get a kind of benchmark or a starting point. And is the performance then adequate for your specific question? If yes, use the model, report the results, share the model, etc. If not, you may change some of the parameters. You can change the hyperparameter grid, and Jenna will give some examples about that later as well. And then you may decide, let's try the other model, and you just iterate through all the models and generate all the results for that. Another option, if you still have a very bad performing model, is to change covariates or add other type of covariates and try that. In the end, it may also be necessary. The conclusion is that on the data that you have at hand, you cannot build this model. So the only option would be to get other data. Nevertheless, even if that doesn't work, our approach is that you should still write the paper and still publish those results. Because there's so much negative results not shared, and I think it's a very bad thing. So there's a lot of publication bias because of that, and you may look it up also in some of the other presentations at OHDSI. Martijn did a very nice overview and showed that there is a lot of population bias and that there's a lot of publications that are just around being significant. And on the other side, actually, we don't see many papers. So we are really focused on publishing scientific results, and I think it's a bad thing. And by standardizing our approaches, we can enforce people just to also publish those negative results, and I think it's better for the field. Also for others that will then try to answer the same question, and will spend a lot of time in trying to predict something that we already knew it was not possible. But all of this, I think, is still research, and we're trying to find approaches to speed this up, especially since in OHDSI we want to do really large studies where we say in a certain disease like diabetes, we want to predict all different types of outcomes that may be of interest to the patient. But not only for diabetes, but for many diseases. So it's a lot of computational time. And if there are methods for us to speed up the process without loss of performance, we should actually go for that, because it simply means that we get the evidence quicker out there. So evidence generation, it's about protocol sharing, CDM, extractions and tools for that, sharing of code, using trained test splits, and selecting the algorithm. The evidence evaluation is then the next step. So how do we evaluate these models? Now, in principle, there are two different measures that we use, discrimination and calibration. So with discrimination, you try to differentiate between those with and without the event. That is, you want to predict a higher probability for those patients that will get the event. That's the ultimate goal here. You want to be able to discriminate between those with and without the chance of getting that event in the future. Calibration is to compare the estimated probabilities with the true observed frequency. And I will go in a little bit more in depth in both of these measures. I think it would help you a lot to understand all the things that we will do in the rest of the day. So this is about a very simple example. Suppose we would say BMI above a certain level would mean a high chance, would say we get the outcome. Now there are two different types of patients here that we want to discriminate. Each of these different patient groups have their own distribution of BMI values, right? So we have a blue and a red type of patients, and we want to discriminate them. And we want to set a certain threshold over those two distributions, saying that everything above the threshold will get the outcome, everything below will not get the outcome. And now we can plot like this table here, and you can fill in the table by saying that if what we predicted and observed is the same, that they will experience the outcome, it's a true positive or a true negative in the opposite direction. But it could also be that we predicted that it would not happen, but it did happen. So it's actually a false negative and a false positive. So I hope that's clear. Now you can calculate two simple things. That's the true positive rate, which is the true positives divided by the true positives plus the false negatives. So it's this one divided by this one, and the false positive rate, which is the same thing for the second row. Now, the receiver operator characteristic curve that you all heard about is actually nothing more than plotting those two different things against each other. So false positive rate and true positive rate as function of where you put your threshold. Right? Now I will have a small animation that is, I think, helpful. Let's see. What happens? Yes. What happens if you move that line? So by moving the line, you're actually moving over the ROC, right? So the more you go to the right, you have a different balance between true and false positives. You make more false positive or false negatives depending on where you move. Now, the area under the RC curve tells you something how well you're able to discriminate those two classes. So if these two distributions become closer to each other, it becomes harder to distinguish both classes. And what will happen simply is that this ROC curve will be closer to the diagonal. With the final and the optimal thing, or not the optimal thing, but the ultimate thing is that they really completely overlap. So you cannot distinguish anybody in the two classes, and therefore you have this line. And it's a completely informative model. And I think it's useful to keep this animation in mind because we read a lot about ROC and area on the ROC, but we just use it as a number. The story behind it is this story. It's just about separating those two different distributions, and the distributions are made by the model that we generate. So I hope that was helpful for you. The other thing is calibration. So that is about agreement between the observed, so what we really see in the data, and the predicted risk. And we want to have a model that has good calibration across the range of all predictions. So also people with a low probability and a high probability, we want to have that very nicely calibrated. So when is a model well calibrated? For example, if, in this case, if we predict a 12% risk that an atrial fibrillation patient will have a stroke in the next year, that we indeed in our data observe that about 12 patients get that, right? So it's what we observe in the data compared to what we predict. Now we can also plot these things against each other, and then you get these type of plots. And you can draw a line if you just make bins. You can create a point, and you can then draw a line through these points. And you can see if your model in general is overestimating or underestimating the risk by comparing it to the diagonal. So if it's more on the top, you have average predictive probability here and fraction in the outcome observed on the y-axis, this means you're actually underestimating and this means you're overestimating. So getting both the discrimination and the calibration is a minimum requirement when you publish a publication to have both of these measures in there. Another important thing, and I mentioned it earlier, is the external validation. So what happens if we build on one data set and then apply it on multiple other data sets and then look at these variables? How well is our model transportable? And that requires things like the OHDSI and the framework. Oh, sorry. And then dissemination. So how do we write a paper on this whole process, on the results? And there's some guidance there, fortunately. There's a nice statement called the tripod statement, and we will have an exercise later in the day, led by Ross, where you will look at a published a publication, actually the CHATS2 publication, and assess whether they actually followed that best practice, the tripod statement, even though we are using that model currently a lot in practice. It has, the list here is a little bit longer. There is a checklist. But what we try to build into our package is that we follow all those best practices and that you have no choice. It will just run it for you. It will generate the output that will be the input for your specific paper. And then, of course, sharing everything. Sharing the protocol, code, models, results on all the database that you run your study. Any questions on this so far? Good. Yes, go ahead.
Can I ask you to go over the ROC part again?
Again?
Yes. Sorry, I accidentally.
I'll do it quickly. Did you get this part?
Yes.
Yes? Yes, it's just, the only thing that I say here is that if you change the threshold, so when I say BMI above a certain value, you move this line and therefore you make more or less false or false negative, false positive or false negatives. The only thing that the ROC curve is just plotting these two things against each other. So the true positive rate and the false positive rate. That creates a curve like this. That's the curve we always assess in all our prediction models. The effect of changing the threshold, so if I move this more to the right, you will see I get less of the red, so I make more errors here. But all the others are correct, right? Because they're all false. So you move actually along this line if you change this, if you move this threshold. Now the question is, in the end, if you build a model, what's going to be the threshold that you will use in the end to make the decision? Because you can say your probability is this high, but you actually have to say to the patient you will get it or not. And you need to decide on a threshold there. And that's what we try to assess here. What is the options that we have on this curve for that specific question? I think, Jenna, you also show ROC again somewhere in your presentation? A little bit, at least the results of it. Yeah. Okay, I'm going to move on. We can talk later together if you want. Yeah, go ahead.
At what point in this process you check you have enough data for feature selection? Because sometimes you don't have enough data to kind of justify the amount of features you put into your model.
Yeah, that's actually a research question that we are working on with one of the students. There are some rules where you say you should at least have for every, like 10 patients with the outcome for every variable that you put in the model. That has been driven by simulation studies a lot. And we are now assessing on a large set of problems if that rule of thumb is actually correct. So what we do is we subsample the data. So suppose you have 1,000 patients, we try to run it on 10, 100, etc. That's a learning curve. There was a poster on that from Henrik John, one of my PhD students. And there we try to assess what's the effect then of the performance. So there's a plateau. At some point you can add more data, but you still get the same performance. It actually doesn't help you anymore. And we can calculate over all those prediction problems if that 10 EV formula is actually correct. It's pretty close based on empirical data, but it's not always true, of course. But so that's something you could assess. But the ultimate test, of course, is those two measures. So if you're able to predict well, and especially if you're able to transport a model well to other data. Okay, yeah. Yeah, go ahead.
Yes, Peter. Thank you. You mentioned that if you do a prediction model and you have, terrible results, poor accuracy, you should publish.
Yeah.
What would you say when you have suspiciously very good results, something like 96, 97% of accuracy? How would you suggest reporting?
Yeah, we don't see that indeed very often. So if it's very high, there's always something like a bell ring and say, well, how is that possible? So one thing that we do in our process is that we will look into the variables that end up in the model. And so, because sometimes there is a proxy of the outcome, a variable in the model, right? So something that's actually almost the same thing, and therefore you get a very high performance. And I don't think that a model like that is valuable by itself. So we try to build in all kind of procedures to avoid that type of too high performance. But the other test is still to do the external validation. And then you may actually see that the performance goes down a lot, which means that it's highly overfitted on the data. I think often in those publications where you see there was not proper internal or external validation. And you can sometimes see it from the paper, but sometimes they don't talk about it, so you don't know that happens. But for me, it always rings, a bell is ringing if it's really that high, and I like to know more about it. Yeah.
Just a couple
Sorry.
comments. Typically we do the same thing in terms of fitting a logistic regression and random forest, because we
Yeah.
want the directionality of the features as well as their importances to report on.
Yeah.
And then two, we normally, I'm always wary about looking at just AUC, because if you have a very imbalanced data set where your
Absolutely, yeah.
target is like 2% prevalence, you just let everybody with 0 get like an 89, 90%
Exactly, yeah.
AUC, so you have to look at other metrics like the PPV and the recall to make sure you have a good
Good
model.
point, yeah. I didn't want to go into that, but you're right. And actually in the package we have position recall curve as well for that unbalanced situation. So you're right. So you can manipulate the position of the RC curve by adding a lot of true negatives in that cell, right? So the precision recall curve tries to look at only precision in recall, and therefore is less influenced by that true negative big cell of patients. So that's why we put it in the package. We're also looking into that problem a little bit because that's again a research question. When do you need to use that approach or the other approach? So by undersampling and oversampling and all that type of approaches, we like to assess on first of all how we can deal with the problem, so how we can build better models if there's a high imbalance between the two classes. I think that's interesting area of research, especially if you can do it on a large number of prediction problems, and then assess whether, in which case, precision recall is better than area on the RC curve. But we have it in the package, and if you run it, you will see it will generate that curve, and you can assess it as well. Thanks for that question. Yeah. Oh, sorry, there was one person in the back that was way early.
When it comes to calibration assessment, how are you assigning patients to the bins? So on the y-axis of that plot.
Right, that's something that you probably, can you, because you implemented that. So getting those bins, can you talk a little bit about that? I may need to get it. Whoever, I'm just looking for the mic. Yeah. Thanks. So the question is, how do we get those bins?
Yeah, so it's just ranked by probability from the model and then split into the 10 different bins.
Yeah.
Also going to say just around the threshold, you can actually think of the threshold as another parameter, hyperparameter in your search space, and then it's another option that you're searching over to find the optimal model to have a good prediction.
Yeah, and there are actually, in calibration space, there are different types of methods as well. So this is like a line, but you can also like smooth calibration, because in this case you draw a line through all the points, and it may actually be that in the beginning it's well calibrated and later it's not, and therefore your line goes way off the diagonal while it's well calibrated in the beginning. So you have smooth calibration curves that Ross has actually been working on, also implemented in the package, by the way, if you want to look into that, where you fit a curve through it, and you can see that actually on the low-risk patients you have well-calibrated model, but later it's not. What's the other question? Yeah.
So AUC is a good way to compare things for model evaluation comparison, but in real practice you have to pick a threshold.
Exactly.
And it's very difficult to try to choose what that threshold is, because you could be choosing things that determine life or death situations.
Yes. Yeah. Absolutely.
Is there any nominal threshold point, also long range, that is considered a reasonable place for health economics?
I'm not aware of anything there, because as you mentioned, it's really context dependent. And that's why actually in the Shiny application that you will see way at the end of the presentation, you can move it and you can see what the effect is on the PPV and all those other variables to see what effect it actually would have if you would take that position or that threshold on your decision choices.
That's a big gap between the machine learning world and actual practices.
Yeah.
Not just relying on AUC to compare aggregate performance, but really getting to a point that actually makes a difference.
Agree, yeah. And actually, I think the AUC is on the whole spectrum of the thresholds. So often, when you're more interested on the lower part of the error seeker, where you may make less errors, depending on the balance between false positive and false negative in your context. But so there are other methods, like taking only a portion of the RC and compare models in that specific set there. But you're absolutely right. So in the end, you have to make a decision, what's the threshold that I'm going to pick? And it may depend on the cost of making a false positive or a false negative. So there are methods also to look into that. I don't want to go into it in this presentation. There are some very nice publications on that. Yeah. So, yes.
Can you comment a little bit about best practices for internal validation?
Yeah, so what we do here is we make a split of the data. We have as a default, I think 75% of training and 25% of testing, or 80-20. It depends, in my mind, a little bit on how much data you have. If you have a very, very large data set with 100 million patients or whatever, it doesn't really matter so much anymore if you make a split of 99%, or because those two groups are still containing a lot of patients which are comparable. So there is some discussion ongoing whether it's still useful to do a train test split when you have very big data. But you could do an empirical exercise, and that is changing that decision, say we use 40, 50, 60, 70, whatever percent for training and use the rest for testing and see what the effect is of that choice. So I don't think there's an answer to the question unless we do the research and run it on large-scale analysis and see what the effect is of that design choice. Yeah.
It's also the number of events.
Yes.
So I think with a lot of these problems that we've been talking about class imbalance a bit, it's also important to make sure you have a large number of patients who actually have your outcome of interest, because often you can have, I've seen you've had 100,000 patients in your target cohort, but only 50 or 80 of them get the event. And then when you're in that situation, how you do your internal validation starts to become sort of more significant. But if you start to get higher numbers of events, it becomes, I think, sort of less and less interesting question.
Yeah, great. Let's see what's for you. Yeah.
My question is on the lines of splitting test and training sets. Earlier you said we can split based on a specific date.
Yeah.
My question is, with observational studies and people coming in at different timelines, even though let's say we're following them only for 6 months, but
Yeah.
they would come in at various points, and when you're splitting it based on the date, aren't you, biasing it
Yeah.
without
Yes, yes. So there's been a nice study, I think it was the Stanford team that did that, when they looked at the effect of time trends, so how models change over time, which is a very nice publication. I don't know the exact title of it, but I can look it up if you want to. That looks at that effect. So if we build a model just using only data of 2000 and then evaluate it over time and how do things change, and that actually has an effect. That they showed actually that does matter. The only thing we here do is that we still do a 75-25% split, but we used a moment in time to make that split. That's the only thing that we do here. But changes over time of the healthcare system will have effect on the prediction, and therefore we should also consider updating these models over time and evaluate them. A very interesting thought is that by putting the prediction model into clinical practice, we are changing clinical practice. So the patients that we see are different than the ones that we trained on earlier. So you may need to update later and see what the effect of that change is. No other questions. I'm just going to continue also because of time. I talked about that. So I want to show you a quick example of a study that we've run earlier, and which is actually one of the questions that we had in the back. So the question here is, among patients with first pharmaceutically treated depression, so a patient that get a pharmaceutical treatment, a drug for their depression, who will get one of the 22 different outcomes. So we'll build a model for all of these 22 different outcomes that would happen within a year. And we evaluated that on 4 different claims databases. And we used all demographics, conditions, and drug use that was available in this data source. So if you look at the databases that we had for the study, those are big claims databases like CCAE, large number of patients with depression. We used, in this case, a time split. We also looked at transportability of, for example, stroke. And we compared 3 different machine learning algorithms, gradient boosting, random forest, and regularized regression. And within these patients, we wanted to predict these 22 different outcomes. So we built 22 different models using this information. And if you look at stroke, so how many got stroke, that's the number of patients that got stroke within that group of depression patients. Now what we created was, using the pipeline, we run all these models, and then we created some nice visualizations, like the one here, where we have a panel per data source. So Optum is a data source, and NDCR, NDCD, and the CCAE database. So these are 4 panels. Within these panels, we have rows that describe the algorithms that we use. So gradient boosting, random forest, regularized regression. And the colors in the cell tell something about the area under the RSC. So it's this discrimination only what we show here, not the calibration. So green is close to 80%, or darker green, or even blue, getting close to 1. And this is one of the outcomes that you see here, which is nice because now we can compare within one database the performance of those 3 models. And we can also see how it would work, how the model is internally validated if we use the other data sources. So in MDCR, we were not able to build a good model for this specific outcome. What's nice about the framework that we have is by adding more cohorts of outcomes of interest, different cohort definitions, we can run it easily for those 22, and you get these type of plots. So now you see for all the 22 different outcomes within the four databases, how the 3 different machine learning algorithms worked. And there's some nice patterns in this plot. So you can see that in general, I think in MDCR we are not able to predict very well, and that may be because of the type of data source. Yes.
Yeah, what data sources?
Can you explain MDCR a little bit? Medicare, yeah. What type of data set this?
So Medicare is like just people who have like supplementary. No, this is just all Medicare people. So it's just a subset of Medicare people. So like poorer US insurance people.
Yeah.
So.
Another thing that we see, which is interesting, is that some of these outcomes we can predict very well in all data sources, and some we cannot predict at all in any of the data sources. And I think that's useful insight, because if we want to invest time, it's probably better to invest some time in predicting stroke and these other things like AMI, and not nausea and diarrhea, which are in general probably quite difficult to predict and very it can have different types of reasons to occur. But in general, if we look at the ones that are above 75%, we were able to predict many outcomes quite well, actually, with this exercise, which I think is interesting. The best one was actually predicting acute myocardial infarction in the CCE database. Another question is, that came up, can we say that one algorithm is working better than the other algorithm? The discussion that we had earlier. And most of the time quite comparable, but there are examples where in this case gradient boosting is performing really better than regularized regression. Now the question is, why is that? It could be that there's interactions between the variables that we did not put into the regression model. But it's interesting to understand how that happens, and also shows that it's a good idea to compare multiple algorithms in doing these large-scale analyses. You could also do external validation, and this is an example of study that Ross has been doing, where you can compare the performance on all different data sets and then externally validate them on other data sets. And so you can have like an external validation plot generated. Now, what did we achieve so far? We've built a package, and we will see all the details in the presentation from Jenna, that can go through all those best practices following internal validation. It's a fully data-driven approach. We can disseminate the models and results, and you will get a demonstration of that. And we can do those transportability assessments quite easily by sending our code to other data sources. Impact on clinical decision-making is still something that we have not really touched upon yet. We've been working a lot on building the framework and building the models. A very interesting step in the future is to find ways to assess the impact of putting those models in clinical practice. And the example presented yesterday from the Danish team in the colorectal cancer surgery is an example where they really want to put it into clinical practice. And they have a very nice option to compare implementing the model in one hospital and not in the other hospital, while they have the same approaches, and see what the effect is. And that's something we have to do more. Currently, we just stop with the data science task, present the model, but it needs to end up in patient care. We can do this now very easily for a large set of target cohorts and a large set of outcome cohorts. Imagine if you have this plot here for many types of problems. This is only in patients with pharmaceutically treated depression, 22 different outcomes. But we can expand multiple data sources, including all the data sources that we are mapping in Europe. It would be fantastic to see if this is consistent across the world. If we can add more outcomes, but also do this maybe for more models, but also for more diseases. So you would have a kind of Google Earth map, a kind of map where you can zoom into a disease, see all the performance, click on a cell, get the model that generated the data, run it on your own data. That would be a fantastic development, I think. I think I'm at the end, and we have a small break before Jenna will take you into the details. There's a lot of nice books as well. Also, the one from Steyerberg, Clinical Prediction Models. There's a new version that's now talking about OHDSI, and I'm proud of that's now mentioned in that book. So have a look at that if you want to learn more, and come back after the break. I think we can take a 15 minutes break. That should be fine. See you later. Thank you.